Welcome back, everyone. In our previous lecture, we explored how electronic and vibrational transitions combine to produce vibrational progressions in molecular spectra. We also learned how the dislandage table helps us to organize complex spectral data into meaningful patterns. But today we encounter another fascinating question. If all these vibrational transitions are allowed, why don't they all appear with the same intensity? Why are some spectral lines extremely bright and intense while others are weak or nearly invisible? This is one of the most important questions in molecular spectroscopy, and the answer lies in a powerful quantum mechanical concept known as a Franck-Condon principle. Today, we will develop the core ideas behind this principle and understand how it determines the intensity distribution of vibronic transitions. To understand Franck-Condon principle, we first need to think very carefully about time scales inside a molecule. And this is where things become truly fascinating. Inside a molecule, electrons and nuclei move on dramatically different time scales. Electrons are incredibly light and nuclei are enormously heavier. Because electrons are so light, they move extremely fast. Nuclei, on the other hand, move comparatively slowly. When a molecule absorbs light and undergoes an electronic transition, the electron jumps from one electronic state to another. But this electronic jump happens astonishingly quickly, typically on the order of femtoseconds. A femtosecond is 10 raised to minus 15 seconds. That is 1 quadrillion, 1 quadrillionth of a second. Now compare this with nuclear motion. Nuclei are thousands of times heavier than electrons. Because of their large mass, they cannot respond instantly. They move much more slowly. These differences in motion leads directly to the Franck-Condon principle. The Franck-Condon principle states electronic transitions occur so rapidly that nuclei do not move during the transition. This means that when an electron jumps to another electronic state, the internuclear distance remains essentially unchanged during that instant. The nuclei are effectively frozen while the electronic transition occurs. This idea is sometimes called Born-Oppenheimer viewpoint. Electronic motion and nuclear motions are treated separately because they occur on vastly different timescales. Now, here is the key consequence. Since the nuclei cannot move during the transition, the probability of a transition depends entirely on how well the vibrational wave functions overlap between initial and final states. In other words, the greater the overlap between vibrational wave functions, the higher the probability of the transition. And higher transition probability means greater spectral intensity. This immediately explains why some transitions are intense and others are weak. Some vibrational wave functions overlap extremely well, others overlap poorly. The spectrum directly reflects this overlap. Because the nuclei remain fixed during the transition must occur at a constant internuclear distance. Graphically, this appears as a vertical transitions on a potential energy diagram. This is why Franck-Condon transitions are often called vertical transitions. Let us visualize this idea. On the screen, you can see a potential energy diagram. The lower curve represents the ground electronic state The upper curve represents the excited electronic state. Inside each curve are vibrational energy levels. Now look at the arrows representing possible transitions. Suppose the molecule initially occupies the ground vibrational level nu is equal to 0. Several possible excited vibrational states are available. For example, nu dash is equal to 0, nu dash is equal to 1, nu dash is equal to 2. Now observe arrow A. Notice that it points straight upward. This is vertical transitions. During this process, the internuclear distance remains unchanged. The nuclei do not move. Only the electronic state changes. This transition is allowed according to the Franck-Condon principle. Now look at the arrows B and C. These arrows are diagonal. Why are they crossed out? Because a diagonal transition would imply that nuclei instantly change their positions during the electronic transition. That would require the nuclei to accelerate and move within femtoseconds. But nuclei are far too massive for that. They simply cannot respond that quickly. Therefore, diagonal transitions violate the Franck-Condon approximation and are not physically realistic. Think of it like taking a high-speed photograph. Imagine photographing a vibrating spring using an ultra-fast camera. The exposure is so short that the spring appears frozen in a place. The same thing happens during an electronic transition. The electron moves instantly while the nuclei remain effectively stationary. Now we arrive at the most important question: how do we determine the actual probability of a transition? And how does that probability determine spectral intensity? To answer this, we must think in terms of quantum probability distributions. On the screen, you can see the probability distributions for vibrational state of a diatomic molecule. These vibrations describe where the nuclei are most likely to be found. Let us start with lowest vibrational state, nu is equal to 0. In this state, probability distribution is concentrated near equilibrium internuclear distance. This means the molecule spends most of its time near the center of the potential wave. The bond oscillates slightly around its equilibrium position. Now consider higher vibrational levels. Nu is equal to 1, nu is equal to 2, nu is equal to 3 and nu is equal to 4. As the vibrational energy increases, the probability distribution changes dramatically. The molecule begins spending more time near the turning points of the vibration. These are the positions where the bond maximally stretched or maximally compressed. Why does this happen? Because at the turning point, the nuclei momentarily slow down before reversing direction. According to quantum mechanics, this increases the probability of finding the nuclei there. Now we combine this with the Franck-Condon principle. The probability of a transition depends on the overlap between the initial vibrational wave function and the final vibrational wave function. If the overlap is large, the transition probability is high. The spectrum line becomes intense. If the overlap is small, the transition probability is low. The spectral line becomes weak. This overlap integral is mathematically known as a Franck-Condon factor, and it is the Franck-Condon factor that determines the relative intensity of the vibronic transitions. This explains an important experimental observation. Sometimes the strongest spectral line is not the 0 to 0 transition. Instead, the strongest line may corresponding to 0 to 1 or 0 to 2. Why? Because those transitions may have better wave function overlap The intensity pattern directly reflects the geometry of the molecular potential. Why the Franck-Condon principle is important? Because the Franck-Condon principle is one of the most powerful concepts in spectroscopy as it connects quantum mechanics, molecular geometry, electronic transition, and spectral intensity. It explains why electronic spectra appear as a structured vibrational bands instead of isolated lines, and it allows us to extract information about changes in molecular geometry between electronic states. Let us summarize today's lecture. Electronic transitions occur extremely rapidly on the femtosecond timescale. Because nuclei are much heavier than electrons, they do not move during the transition. As a result, electronic transitions occur vertically on a potential energy diagram. The probability of a transition depends on the overlap between vibrational wave functions in the initial and final states. Greater overlap leads to higher transition probability and stronger spectral intensity. This wave function overlap determines the intensity distribution observed in vibronic spectra. In our next lecture, we will examine specific examples of good and poor wave function overlap. We will visualize how the shapes of potential waves influence the spectral intensity patterns and learn how Franck-Condon factors shape real experimental spectra. Thank you for watching. I will see you in the next lecture.